Okay, so we're going to pick up with lecture 11, and then 12 is also open. So I'll work some of these homeworks really quickly today too. I don't want to spend a lot of time with this, okay? But I also put this supplemental material out here for you. There's just a boatload of information out here, really good stuff about how to do certain things. So you should look this over. Besides, you have the lecture notes. You also have these sample homework problems, and then you have some other supplemental material. So make sure that you look at that, okay? So let me pop up kind of what we did last week. I think this is the stuff. So this is really what we did out in the field. Let me, all right, so let's see. We talked about all of this last week. Let me grab my slideshow. Okay, so this is the material we went through last week. And so we're gonna just pick up with this and then move on. So we talked about basically doing horizontal location, okay, this is kind of what we were dealing with last week, tangents and curves, and we did a simple curve layout. Okay, so this week we're gonna pick up with profiles and cross sections. That's why I said some of this I'll be able to pick up and do on Thursday, because I guarantee it'll probably take no more than an hour to go out and run those levels. In fact, if we take that long, that'll be more than enough. So we'll do that, and then we'll talk about these cross sections and those kind of things as well. Okay, but let's get into the curves themselves. Now, one of the big things we talked about was stationing. So make sure you understand stationing. Just remember, it's a horizontal distance along an alignment, and so you always have a beginning point, and you're just following it like a number line, more or less. So station 12 plus 7201 is 1,272.01 feet from your beginning point. And when we hear the term full station, half station, or quarter station, that's an interval based on 150 or 25 feet respectively. What was the interval that we staked our curve out last week? Anybody remember?
25 feet.
Yeah, which is very standard, particularly on highways where you're doing curb or even just edge of pavement, just stuff that doesn't even have a curb. You're going to do it like usually every 25 feet. So you guys should think about that and appreciate that. If you think about an interstate highway that just might be 400 miles long, at some point there was probably a stake every 25 feet along that thing to govern how that thing was being built. So that's a lot of work that got generated. So go ahead.
I understand like how to read the plus, like the plus and everything, but yep. Why did they do that instead of just putting 25.63 on everything? Why did they put the plus in after it? Is there a certain reason why?
It's just a separator. I'm not sure exactly the reason. I just think it made it easier back, to see that. So it just, yeah, it's just like putting a comma in, like we do. It's just a way of separating the data. But a lot of times, if you're between station 12 plus 00 and 13 plus 00, a lot of times I'll just say plus 72.01. So it just makes it kind of a shorthand way of dealing with it. You see what I'm saying?
Yeah, I get it now.
So it's just, it really is. I don't know exactly where it was derived from. To be honest with you, it probably came from railroads, because railroads were around before highways were. So a lot of the stuff that we deal with in highways came from railroads initially. So you would probably have to go back and look at railroad engineers. And of course, full stations, one full station, that was based on the steel tape that they use. It was a 100-foot chain, what they called an engineer's chain back in the day. So that was kind of where all those numbers came from. Okay. Another thing you'll see very often on highways is a right-of-way will be 66 feet. Does anybody know why that says 66 feet for right-of-way? Because the original surveyor's the original surveyor's chain was a 66-foot chain. So you had one chain of width on a highway. So that, again, a lot of that just goes back to what they were using. So that was a great question. I really don't have the answer, but I would think it probably came as a derivation from railroads. All right, so remember left and rightness, that's also, left or right station. We have to deal with that a little bit on our grading stakes this week. So that explains that right there. That picture is good. So let's jump into the curves themselves. I want to go through this. So we basically laid out what was called a simple circular curve. So it's basically you've got a tangent that comes into the curve starts and then it ends, and then you got a tangent out. So that's probably 80% of highways curves that you're encountering are like that. We talked about some other ones, but we're not concerned with that. So let's go into the curve itself. Curve is composed of 8 elements: the central angle, the radius, the tangent, the long chord, length of arc, degree of curve, middle ordinate, and external. These last two, the middle ordinate and external, are almost never used. In fact, very often you don't even see them on a set of plans, but you typically will see delta, RT, long chord, length of arc, and degree of curve. Those are all working numbers that are really prominently out there. Of those 8, how many do you actually need to define a curve? Does anybody know? You've got 8 elements. You don't need all 8 elements. How many do you actually need to define a curve?
2.
How many?
2.
Correct. Now, when you say that, and this is important, Casey, I could give you 2 elements that you would not be able to solve that curve with. If I gave you the degree of curve and the radius, that would be an unsolvable thing, because basically the radius and the degree of curve are the same thing. Okay, so they have to be somewhat independent. The 2 typical values that a lot of people use are going to be the delta angle, the central angle, and the radius. Those are the most common. Okay. So then there should be a pretty good picture, and I think, also these stations are important when you talk about curves. PI, PC, and PT, those are very important. So we actually staked out in the field, we staked out a PC and a PT station, and we did that via radial stakeout, and then we deflected the rest of the curve in. So we basically produced POC stations along that curve at 25-foot intervals, okay? So this diagram is a great diagram. It's going to show you how everything interrelates. You got your tangent coming in, that's referred to as your back tangent, your PC station. Then the distance from the PC to the PI is called T. And then you have PI to PT, that's your T distance also. So these guys are always symmetric, it's always the same, unless you have what's called a non-tangent curve, but we typically always do tangent curves, okay? Length of arc is your distance along this thing, like that. That's your bent distance, and the long chord would be like if you shot from an EDM PC to PT, what you would get is long chord. Delta, the central angle here and here, it's the same angle, again, because of the symmetric aspect. Degree of curve is the angle that subtends 100 foot of either arc or chord. So it just depends. Highways use what is called a degree of curve arc method. And so that means that their angle that they're giving you is a distance of 100 feet along the arc. Okay, railroads always use a chord definition, and we're not going to be concerned with that. So here's your major equations. Does anybody recall, did I run through an example with you guys using this last week or not?
Yeah, you did.
Okay. All right, so those homework problems, and we might want to work a real quick homework problem, just gives you kind of these things. So we'll take a look at that real quick. You don't need to memorize these guys, but you do need to know how to use them, okay? So I definitely do not expect you to memorize them. But some of them are really pretty simple. So like T, tangent is your R times the tangent of half of delta. Long chord is 2 times the radius times the sine of half of delta. And then arc length, you have several different equations. You could really, for a highway, you can either use this delta pi r over 180 or this 100 delta over degree of curve relationship. Those would work. But on a railroad, you can't use both of them. You have to use this one right here. But again, we're not considering railroads. Another set of equations that I gave you, the degree of curve, there's your arc definition. And then those 2 called middle ordinate and external secant. Don't be concerned with them because we're not going to use those too much. Although the book has a couple of problems that might deal with that. So, you know, just kind of look at them. It's just algebra. It's not that tough, really. So I believe then, if what I saw, we went through this problem, is that correct, you guys? The other day?
Yes.
Okay. So let me take a problem out of the book real quick. We'll work through it and then see if you guys can solve it. And then if you have any other questions while I'm doing this, then don't hesitate to ask.
Can you give us the formula for the short chord too?
Yeah, we'll get to chords here in a minute, okay?
All right.
Because what I want to do is first do a couple of curve problems, okay? And then I'll come back and do the chord stuff, layout, okay? So
All right.
hang on to that and make sure I get to that for you when we're ready to do that, okay? Casey, did we do any solutions on the short and long chords last week? Deflection angles, did I show you guys how to do that? Can't remember.
We did one for the long chord, and then like
Okay.
2 or 3 slides back, you had a bunch of formulas, and it had the long chord on it. It didn't have the short chord. That's fine.
Did we solve deflection angles? Do you recall?
Look back at my notes.
Okay, yeah, let me know because I can't remember. I've got so much rattling around right now. Did I do if we would have done a deflection angle problem, it would have been on this problem right here. Does that ring a bell?
I don't see anything with the deflection angle on.
Okay, so we'll pick up and do that then. Okay, so I'll come back to this problem. Okay, I'm going to do one out of the book real quick. All right, so this is one of the ones I asked you to do. So I'm going to work this one with you. Let me jump over to this this guy here. All right, so what I'm looking at is, let's see, problem, oops. See, I'm looking at problem, let me see, I gave you 1 and 6. Let's look at problem 6. This is problem 6 out of your book. It would be page 1650 if you have that. So what he gives you for 6, let's see. Wait a minute now. Hold on a sec. Trying to find what I have here. Not finding what I wanted. Well, for some reason I can't find what I'm looking for. On curves. Okay, well, let's check this one out. So I think this is problem 6 out of your book. What they give you is the radius for this problem. And he tells you that the radius is 441.01 feet. And he gives you the long chord. So that's 275.87. Okay, that's what you're given. And what you need to calculate is delta. We need to calculate the T value. We need to calculate the L value. And ultimately, you could also calculate degree of curve. And if you wanted, they could give you middle ordinate and external secant, but we don't need to do that. Okay, so this is not traditional type of problem because what we're given here is radius and long chord. So you have to back into this. So anybody know how we would start this? This one's a little tough because you don't have what you would normally want. So by the way, this is problem 6 out of your book. So how would we start this? Okay, a little hint. One of the things I need the most is this guy right here. So does anybody know how we can solve delta? We have the radius and the long chord given. So if we look at the equation for the long chord is equal to 2 times the radius times the sine of half of delta. Notice what we have here. We have this and we have this. So what we can do is rewrite this equation. So we can say that the sine of half of delta would be equal to the long chord divided by 2 times r. Does everybody agree with that?
Yep.
Okay, so what we really want is delta. So if I have sine on this side, I'm going to take the arc sine of the sine, and that's going to give me delta over 2. If I take the arc sine of that, then I have to take the arc sine of this. Everybody see what I did algebraically? So looking at this, then I went to this, taking the arc sine of both sides gives me this. And I really don't want half a delta, I want full-blown delta. So it's going to be 2 times the arc sine of long chord over 2 times the radius. So if we plug that in, let's see what we come up with. Long chord, 275.87 divided by 2 times the radius, which is 441.01. Okay, you guys plug that. If you got calculators, once you calculate that, see what you come up with and verify me, okay? I don't think I got mine right.
I hope I did it right. I got 36 degrees, 27 minutes, and 9 seconds.
That sounds good. That's what I came up with too. So that's perfect. So we're coming up with a delta of 36 degrees, 27 minutes, and 9 seconds. So you have to be kind of careful how you're doing it, okay? Especially when you're keying something like this in your calculator. So up here now we have one of the solutions that we need right there. So that's pretty good. So that's a little tricky because you have to back into it. That's not real typical. But that's, you know, what he's trying to get you at is if you have information, you can solve other things, okay? So degree of curve is real easy to get. Anybody remember how to get that? In fact, we wouldn't have even needed delta. If you look back, there's an equation for degree of curve that says 57, 29, 578. A lot of people just use 58, but when you do that, it refines. It's a little smaller. So that's divided by the radius, 441.01. So the degree of curve of this, now remember that's expressed usually degree minutes seconds. So 57.29.578 divided by 441.01. And that gets me like about 12 degrees, 59 seconds, 59 minutes and 31 seconds. So we've got this guy, 12, 59, 31. Okay, so what about t? T is real easy. It's just r times the tangent of half of delta. So now that we know delta, we can solve this pretty easily. So that would be 441.01 times the tangent of half of the 362709 number. And that's half of that. Sometimes people have two numbers here of angles. Sometimes they'll use the wrong one, so be careful when you have both given. delta is definitely never equal to degree of curve, okay? They're separate, completely separate things. 36, 27, 09. We'll take half of that. I got a tangent of 145, 22. Does anybody agree with that?
That's what I got.
Okay, so that checks. And L, now you've got several different ways you could do it. We could either say delta pi r over 180, but that's also equal to 100 times delta divided by degree of curve. So you could do it either way. Well, let's see what we come up with. Now, they might be slightly different because you have a little bit of rounding going on in your degree of curve number. But usually it's not that big of a deal. Maybe they'll be off a hundredth or two between the two. Let's see what we come up with. I'm doing the delta pi r right now. If somebody's doing the other nut, you might get slightly different. Looks like 280.58 feet. Okay, so there's everything. So if you do these out of the book, they're going to be giving you, the author is going to be giving you 2 elements out of those couple of those problems and then wants you to solve the remainder. I'm not going to worry about middle ordinate or external secant. Like I said, most people don't use those, so that's not that big of a deal. Any questions on that? That's a typical type of problem that you guys will encounter. Okay, any questions? Well, let's try one more. I'm going to try number 18 out of the book, okay? That was another one I assigned you. And it tells you that they're giving you a length of arc for the curve and the degree of curve, and they want to know what the central angle is. Okay, they want to know what delta is. So let me solve what we've got here. Okay. So this is problem 18 out of the book. Again, this is in page 1650. So it tells me that I have a length of arc L is equal to 410 feet. And he also gives me the degree of curve. And we're assuming, of course, this is a highway. Tells me that it's 21 degrees flat. Also tells me that the PI station is equal to 155 plus 7542. Wants to know what delta is. Okay. So who can tell me how we solve this? This one's real simple. Well, what do we know? We know this, and we know this. Do we have an equation that relates these two together with that? I just got finished using it. There's one that says L is equal to 100 times delta divided by degree of curve. Can we use that to solve this?
I think so.
Absolutely. Look, we've got this given, right? We've got that given, and that's a constant. So we can solve this for delta by saying that that would be L times degree of curve divided by 100. Did I do my algebra right there, everybody?
Yeah.
Okay, so what's that say? L is 410 feet times degree of curve, which happens to be a nice even 21 degrees divided by 100. So let's see what we get. Now remember, you're going to get a decimal degree, so you're going to have to further take that into degree minutes seconds, okay? So most of the time your calculator is going to give you decimal degrees. So I get, here's what my calculator tells me. My calculator is giving me 86.1000. I wouldn't usually use that as my answer. What I would want that expressed in is the degrees minutes seconds. So your answer would be 86 degrees, 6 minutes, and 0 seconds. That's what I'm coming up with. Anybody agree with that? Anybody get those numbers?
I agree with that.
Okay, perfect. What did this have to do with the problem? PI. Did that have anything to do with the problem? Did we use it?
No.
Nope. This is what you call extraneous information. It really didn't do anything for us. It's probably there more to trip you up than do anything, okay? So a lot of times people will see, you know, hey, they gave me 3 things or 4 things and I need to use all of that, and that's not always the case, okay? So you have to kind of pay attention to that. All right, so curves can be tricky because of that. Check those problems out again, the ones that I assigned last week. You should be working on those. That's what we're going to be looking at from a quiz standpoint, something like one of these, okay? So let's go back then. We'll come back here and do some more problems, unless anybody wants to do anything else before we move on. All right, so let's go back to the PowerPoints. So we solved this stuff the other day. Okay, so this is what we were talking about. And Casey, this will get into your problem or question. For curve layout, you have different methodologies: deflection angle long chord, deflection angle and short chord, and coordinates by radial stakeout, which is, by the way, what a lot of people use. Now, I tried to explain to some of you guys last week when we were out there laying this out, is that a lot of people use the radial stakeout method, but actually the chord method, long or shorts, can be a lot quicker if you set it up right. The only downside is this could take you maybe two people or 3 people to do it. But if you have a robotic total station, you can probably do a long chord method just by 1 person. So, but this probably gives you a better curve than this. Why is that true? Why is radial stakeout not exact, not perfect?
Isn't there error?
Sure, there's error everywhere, right? And in terms of angle, in terms of distance, in terms of calculation. And the thing is with radial stakeout, there's real no check, okay? So if you put every station in except, like, say, one of those stations, radial stakeout will be good except for that one station, but there's not a really good way to check it typically. By utilizing the long or the short chord method, when we get to the end of the curve and we check into the PT or the PC, depending on which way you're deflecting, you kind of have a check. It's kind of like a closure. So yeah, I'm not arguing one method or the other. I'm just saying they're all good. But sometimes these guys can be quicker and there's a little bit more of a check. Okay, but you have error associated with everything you do in terms of angle, distance, and all of that, right? So this is the kind of method we use primarily for most of the curve, where we were occupying the PC. We were turning a deflection angle and going this guy, which is called a long chord, long chord, long chord. And we actually got to set up on the curve, backside the PC, and then continue. And some groups, I had you guys do long chords from that point. Some people, we did short chords. So this is where we're going to explain how to do this, okay? So let's go to the next picture. This is the short chord method. What you're not seeing here is the deflection angle from the PC. It would be kind of involved to show it on this picture, but there's actually an angle being turned from the PC to each of these points. But the distance is being measured from the stake that you preceding the one that you're staking. So that's kind of cool the way that works. So here's your equations when you do any kind of layout. So first you need the deflection angle, and that is based on the distance L, which is your length of arc times your degree of curve divided by 200. Now what's cool about this, you're going to be doing different stations, but you'll be set up essentially at one spot. So L is always the distance from where you're sitting to where you're going. That's why I'm using the term delta stations, which means change in station. In this equation also, which is kind of cool, degree of curve divided by 200 is never changing. So that's a constant for this curve. The only thing that's changing is L. Okay, so it's just the L distance. So we're going to set that up here in a minute. So the long chord equation, and this gets to your question exactly, Casey. The long chord equation is based on 2 times the radius times the deflection angle to that station. The short chord is the exact same equation. The only difference is instead of the deflection angle, you're using what's called a deflection increment. So that would be the deflection angle from one station to another instead of the deflection angle from the PC to that station. So really, all we do is just subtract one deflection angle from the other, and that's the deflection increment. So I'm going to go through this to show you exactly what I'm talking about. I don't think I'm not sure if this next slide has it. Yeah, here we go. So this is showing you the relationships between your deflection angle and your chord, okay? And there's your equation for that. So let me see if I've got this. This might be the end of this. Okay, so we're gonna do a little problem here, okay? I'm gonna do some deflection angles with you, and we're gonna do it for the curve that we laid out well, not the curve we laid out in the ground, but the one we did on the lecture here. So let me flip back over to this, and I'm going to start a new picture. Okay, so last week we did that curve where we had calculated information. So I'm going to give you what we know. We know that the delta for this curve, that was given. Let me go back and get that. The delta for this curve, and we did this last week, was 16 degrees, 42 minutes. We were also given the radius for this curve. That's 1,000 feet. And we knew the PI. So the PI station was given. Okay, this is what we were given. And then what we're going to do is do the layout for this curve. So we had calculated a couple of things last week. Okay, I could go back through it if you need to, but we calculated the T for this curve to be 146.78 and the length of arc to be 291.47. Okay, so we did this last week. So we calculated also the PC. So how do you calculate a PC? Anybody remember? Or look back in your notes. PC is given by what equation? If I draw
PI minus T.
There you go. PI minus T. So I'm going to take the PI station minus the T distance. So that would be what? We've got 2563.40. 2563.40 minus 146.78. So that gets us 24 plus 16, 62. So this is the station we're sitting at. PT is given by what equation? Look it up in your notes.
PC plus L.
Yes, PC plus L. So the PC station plus your L distance. So Notice we had to calculate both of these things because those were the only things that were given initially. So we know that it's 2416.62. We're going to add to that 291.47. That gets us 27 plus 08.09. Okay, so I think we came up with these last week. Now the other thing we're going to need to know for this curve is the degree of curve. Okay, so degree of curve is 5729.578 divided by the radius. 5729.578 divided by 1,000 feet. And that'll give me a decimal degree. Our degree of curve is 5 degrees.
43, 46.
43 what?
46.
Okay, I got 46. Yeah, 46. Now, it's not actually 46, is it? Whoops, I just, I said 46 and wrote it down wrong. It's not actually 46, is it? Mine's like 46.48. So there's rounding going on there, okay? So I want you to understand that. All right? Is everybody okay with that so far? Okay, so we're going to occupy the PC and deflect towards the PT. So if I was drawing a picture of what's going on here, I'm saying I'm at the PC and I'm working my curve around until I hit the PT. Okay. Now you could do this method backwards. It really doesn't matter. You just have to know where you're setting and where you're going. Okay. So that's what we're doing. We're setting at the PC, we're occupying the PC, and we're going to deflect around this curve. So you set up a real simple chart. I guess I don't think I did show you this last week. So we're going to go through all these numbers. Hopefully if we did do this, this won't be a bad thing because it's good to know this. So you have a station column. You have a length of arc column. Hopefully this looks familiar because these are the sheets of paper that I handed you guys out in the field. We have the d/2 angle, the deflection angle. We need the long chord to each station, and we're going to calculate the short chords. Okay, so this will get your question direct. So we're going to start where we're occupying. This is 24 plus 16.62. Okay. So we need to know the interval that we're going to cut this curve into. So what was the interval we did out in the field? We said 25 feet, right? Is that correct?
Yeah, we did 25.
Okay, we're not going to do that now because we don't have enough time, but I'm going to do this to every 100 feet, okay? So what would be my next station at 100 feet? What's the next station at 100 feet?
It'd be 25 plus 16.62.
Okay, you could do that, but that's not the way most people do it. They don't want to go to an uneven station. They want to go to a full half station, quarter station, or full station. So the next full station would actually be 25 plus 0, 0. You see what I'm doing? So this isn't exactly 100 feet, but I'm going to a full station because I'm keeping it simpler. So then I'm going to go a full 100 feet. And then I'm going to go a full 100 feet. And then I'm going to end at this station, which is not a full 100 feet. This is at 27 plus 0.809. Do you see why you do this? So that you keep these stations right on the pure stations. So you're getting pure full stations, quarter stations, or half stations. Everybody see that?
Yeah.
Okay. So we're sitting on this station, so there is no distance, there is no arc, there is no chord, there is no short chord, okay? So L is defined as the distance from where you're sitting to where you're going. So how do we solve that? If I'm sitting at 2416 and I'm going to 25, how do I do that?
25 minus 24, 16.62.
All right, so 2,500 minus 24 plus 1662. So what do we get?
83.83.
Okay. 0.38.
Yeah, 3.8.
Okay. You said 8.3, didn't you?
Yeah, I did.
Okay, no problem. I just want to make sure because that's what I thought I heard. All right, so what's the next distance? The next distance is from where you're sitting to where you're going. So all we really have to do is add what? 100 feet to that, right? Right?
Yeah.
And now we're from where we're sitting to where we're going. So now we're out 283.38 feet. And then last, when we subtract these two, what should we get? L, 291.47. Okay, is everybody okay with that?
Yeah.
All right, not too hard. This is the thing that sets everything up, okay? This is the important guy right here. All right, so now we're going to use this equation to solve those deflection angles. D over 2 is equal to L times degree of curve divided by 200. So the only thing that's changing in this equation every time is L, because the degree of curve is a constant for this curve, right? And 200 is a constant. So what you can do in your calculator, you can take degree of curve and divide it by 200 and just store it, and then just multiply times recall to get those different numbers, okay? I can't do that on my calculator because I'm haven't figured out how to do storage, so I'm going to have to key it in each time. So let's do that first. We're going to take 5 degrees, 43 minutes, and 46 seconds divided by 200 times my L value, and let's see what we get. I'm going to use the L, the first L, 83. Okay. You guys let me know what number you got.
223. 19.
223.19. That's what I agree with that. That's good. Anybody else that's doing this? That's what you should come up with. Okay. So let's do the next one. So we're going to take 5 degrees, 43, 46, divided by 200 times the next L. And it looks like I'm getting 5 degrees. So you'll notice because L is increasing, these numbers are increasing. Okay. That's what I came up with. 5 degrees, 15, 12. Anybody agree with that?
That's what I got.
Okay, cool. Let's do the next ones. I'm going to go ahead and just calculate them. You guys let me know. It's just really, once you get it set up, it's pretty much plug and chug, okay? The only thing you can typically do, which is easy to do, is just fat finger something in when you're keying it in. But as long as you have your degree of curve right and your L's, you're going to get the right numbers. Or you should anyway. And I did something wrong. I'm talking, so I didn't do it right. I got 8 degrees, 7 minutes and 5 seconds. Does anybody agree with that?
That's what I got.
Okay. And let's go for the last one.
I got 8 degrees, 20:59.
Okay, 8 degrees, 20,
Yeah, 20.
59. Okay. Now, does that look like familiar at all? This number right here? Look at
Half
delta.
a delta.
It's half a delta. This should be half of delta, okay? If it's not, you did something wrong. Now, that's not exactly half a delta. Why is it not exactly half a delta?
Isn't delta rounded?
Not delta isn't rounded. What's rounded is this guy right here.
Oh, yeah.
That's the thing that's rounded. And see, because he's in this equation, see that? it's giving you just a slight a bit of rounding. Remember I said this isn't exactly 46? And that's what's going on there, okay? Is everybody okay with that?
Yeah.
So if I get a number like this, that's close to half a delta. That checks for me, okay? I'm good with that, all right? So now we've done most of the work, okay? So the rest of it now we're going to calculate chords. So let's calculate the long chords first, and then we'll come back and do the short chords. So Casey, I'm getting your question answered here shortly, okay? But really, the long chords and the short chords basically is the same equation, okay? So for the long chord, if you will, just the chord, long chord, it's 2 times the radius times the sine of the deflection angle. So all you do, now don't divide this number by 2. It's already divided by 2. So you just literally plug that in, plug that in, plug that in, and you're multiplying. In this case, it's very simple. The radius is what, 1,000? So you're just multiplying by 2 times 2,000. So let's see what happens. So we're going to take the sine of 2 degrees, 2319 times 2,000. And I get 83.35. Why are these numbers close, but they're not exact? Why are we getting that? Is that rounding? What do you think? Is it rounding causing that? Or is it because of the nature of what you're measuring?
I think it's because we didn't do the full 100 feet for that first station at 25 to make it an even number. So it's
No,
not that.
that's not it. That's not it.
Oh.
Anybody else? Here's why. Because you're measuring 2 completely different things. What is L versus long chord? What's the difference there? Well, you have an arc, right? And you have a chord. The distance from here to here, which in this case is what, 83.35, is different than the distance here, which is 83.38. Can you see that now?
Yeah.
Why are they close? Because this angle is pretty small, okay? As these numbers get bigger, watch what will happen. These numbers are going to get further and further and further apart. Is everybody okay with that? Because we're measuring chord lengths, not actually arc distances, okay? But we calculated it using arc distances. All right, so let's go see if we can calculate the rest of these quick, okay? Should be able to. Some of you guys might already have them already. If you do, just let me know. So we're going to use this equation continually to do the rest of these. So let's see what we come up with. So I've got, for the next one, it's going to be the sine of 5 degrees, 15 minutes, and 12 seconds, okay, times 2,000. So I got 183.12. So that's got a lot more difference because the angle's bigger, okay? We're going a longer distance, so we're going to expect more difference, okay? Watch what happens when we get to the next couple. Let me know if you're not getting those numbers, okay? We'll verify it. You got 280 to 43. Okay, so again, notice how it's starting to change quite drastically. Then the last one, has the biggest amount of deviation, 290.43. Okay. what you guys will definitely notice with this, the smaller the radius is, the more these are gonna disagree, okay? The larger the radius is, the more these are gonna agree, because it has to do with the size of the arc. Is everybody okay with that?
Yeah.
Okay, so now we're ready to do short chords. So look, we have 3 short chords here, okay? 3 short chords. The first short chord is the distance from the first, where we're sitting to where we're going to that first stakeout. The first short chord is always equal to the first long chord, so all you have to do is write this over here. You don't have to calculate anything. The next short chord is the distance between 25 and 26. 26 and 27, okay? So those are based on 100 feet. So this is going to be pretty close to 100 feet, but it won't be exact, all right? Is everybody okay with what I'm saying?
Yeah.
The last short chord is based on this distance from 27 to 270809. So the distance is 809. So basically 8.09 is going to be the number we're going to be looking at. So here's the question that we were looking at all along. How do we calculate short chords? Well, for the first short chord, it's already calculated. For the next short chords, if they're based on 100 feet, this distance, this angle right here is going to be the difference between these two guys, or the difference between these two guys. They should give you the same number. So if you subtract 2 degrees, 23 minutes, and 19 seconds from 5 degrees, 15, 12, I get like 2 degrees, 51, 53. Is anybody getting that number? Two degrees, 51, 53. So I just subtracted deflection angle from deflection angle here. Or I could do that too right there. Anybody get that? 2 degrees, 25, 53? Nobody got it?
Yeah, that's what I got.
All right, so that's called your deflection increment. That's the amount it's changing from here to here. If you notice that number, 2 degrees, 51, 53, it's actually half of this right here, which should make sense because if this is 100 feet, the deflection angle is always half of that angle. So this is going to be half of that, essentially. So we're going to take that 2 degrees, 51, 53, that increment, and we're going to plug it in here. So for the short chord, this equation would say this. Your short chord is going to be 2r times what's called your deflection. We would call this deflection increment. That's the amount it's changing from station to station, okay? So the increment, again, is just the difference between 2 deflection angles, okay? So I subtract that, plug that in there and take it. So let's see what we get. We're taking the sine of 2 degrees, 51, 53, okay? Anybody get a number for me?
99.96.
So does that make sense? It should be close to what? It should be
100.
close to 100, right? Because 25 to 26 is 100 feet, and this is saying it's 99.96. Well, the chord always has to be less than the arc, right? Is that correct?
Yep.
Okay, so the distance from 25 to 26 along the chord is 99.96. What's going to be the distance from 26 to 27 along the chord?
It'd be the same thing.
It'll be the same, so I just usually put a ditto mark in there. And you may have that all the way down for a lot of successive stations, okay? That makes sense?
Yeah.
Okay, so the last deflection increment is based on the change from this deflection angle to that deflection angle. So all we're saying is we're going to subtract those 2 angles, plug them into here, and we're going to calculate it. And I'm going to tell you it's going to be really close to that number. In fact, it might be exact because it's a small arc. So the difference between the arc and the chord is probably going to be negligible. It's not going to be there. So we're going to take 8 degrees, 20 minutes, 59 seconds, subtract from that 8 degrees, 7 minutes and 5 seconds. That gets me a deflection increment of 0 degrees, 13 minutes, and 54 seconds. So we're going to plug that into here, take the sine of that times 2000 and see what we get. And I basically get, well, that's a little off. I get, no, it's actually right on it. It is 8.09, okay? So there's how you do your layout. And it's really simple. And basically we're saying we're going from the PC to the PT, but we could go from PT to PC. We would just start here and work backwards. These angles would have to be recalculated, and so would the chords, but very simple process. Are you guys seeing how that works now? Everybody get that?
Yeah.
Does that answer your question, Casey, about the deflection increment now and the short chord?
Yeah, it's pretty simple now. I remember you were showing us in the field in the lab because we couldn't see over the hill and we started doing it.
And we were doing it really quick.
Yeah, and I wanted to like dive into it a little more.
Absolutely, absolutely. And you can see this chart really does all your work, okay? And you have two equations basically. This equation is this is like doing all your work. And then this basically equation here, long and short chord is essentially the same. It's just what you're calling your angle. It's either the full-blown angle or the increment, okay? So you really have three equations. And basically, it's just 3.5 if you want to think of that being used several times. Okay, does that make sense now? When you put that stuff all together, it's actually pretty simple to do. And it's kind of, I think you guys all got a nice eye opener on how that worked out in the field. It's actually pretty neat, right? You guys agree?
Yeah.
Okay, cool. All right, no questions on anything else before we move on to the next section. We're going to talk about vertical curves now, okay? We're all good?
I'm good.
All right, I'm gonna work back then. And so we had the other day I showed you a set of highway plans, which were pretty neat. These guys right here, and we're looking at a lot of busyness here. But what we've been focusing in on, and what we've been focusing in on here was the horizontal alignments. Okay, so we're looking at center line here. Now this happens to be an intersection. We're going to be laying that one of those guys out next week. Not like this, obviously. But you notice, you should start to understand what all this is saying. And notice here we've got PI station, delta, degree of curve, radius, T, L. All of that stuff is talking about this curve for State Route 747, which is this curve right here. And then you'll find another center line curve data right here. This is for Tylersville, and that's the one right here. Like I said, if any guys know where this is the actual set of plans they used to build this thing back probably about 20 years ago. So this is called your plan sheet. That's what we've just been talking about, plan view objects. Now we're going to dive into this guy here. This is your profile. And your profile has a lot of stuff going on it. But basically, you're talking about what's happening in terms of grades, okay? Elevations. And so you have a center line profile, and you also have existing information. So remember, we said the dashed information is existing, and the proposed information is solid. So what I'm looking at here, we're going to look at this thing called proposed center line profile. And you'll notice it's got a line that comes up. It's got this junction where it meets. That's called a PVI. It's got a station. Then it's got this line going out. And they relate these guys into what we call percent grades. And then you down here, you have this thing called VC that stands for vertical curve. And what we're going to do is show you how those guys work. Okay, so that's what we're going to talk about. So let me grab my PowerPoint stuff here. Let's see, I think that's the wrong one. Let me go to the other one. Okay, so this is going to deal with vertical curves. Okay, so I have a little bit of redundancy in here. Let me weed that out. I'll go through this real quick. So you guys have this now. So we want to concentrate on vertical curves, reading those plan kind of things. and doing some vertical curve calculations. And so that's what our lab's going to focus on. We're going to talk about grades. How do we do that? So on lab 5 and 6, you have a profile on there that goes along with the alignment that we laid out. And that's what we're going to be dealing with, grading that thing on Thursday. So we've talked about providing line. That's what we just showed. Now we're going to talk about grade. And then there's this other thing called cross-section. And now I don't know how much I'll get into that today, but we'll take a look at that as definitely on Thursday. So plan view, remember, is giving you line primarily, station offset information. Grade is provided by the vertical plane situation. You get a station and an offset, or a grade and a slope, and that's called your profile. So this is a really basic, simple profile, but in this profile, the numbers across the bottom in green here, these are your stations. So this is increasing from 0, that's the beginning point, to the end out here. And the green line up here, that's your existing ground line, and this line right here is your proposed line. And this information in cyan is information that's relating how this proposed goes together. On the left side here, this is elevation information. Okay, cross-section is a vertical plane that is going perpendicular to the alignment. It's also referred to as a typical section. So this is a graph, again, that relates offset, elevation, and slope data. So this is your center line out here where it says curb datum. And what it's showing you is from the center of the road to the back of the curb. They're giving you a curb datum, and they're telling you certain pieces of information. They're telling you from the back of the curb to the face of the sidewalk that that's sloping at 1 inch per foot over a distance of 6 feet. They're showing you your sidewalk is sloping at 1/4 inch per foot for 4 feet. By the way, sidewalks, that's a typical number, 1/4 inch per foot. So that's pretty standard. And then out here, we're getting these things called 2-to-1 slopes. So this is telling you how far it's going to, or what rate it's going to increase at up or down, and how far it's going to go until you hit existing ground. So this is called a typical section. And these are really, really important when you particularly get to highways. We're going to work with these a little bit also on Thursday. Okay, so I probably won't get to those too much today. All right, so let's, got some redundancy in here. I'm going to buzz through that. Okay, so roadway profiles, okay? When we talk about the roadway profile itself, the roadway profile contains 2 major features, just like the horizontal alignment plan view. We call them tangents and curves. In a profile, they're called gradients and curves, okay? So a gradient, another name for that is a vertical tangent. Some people use the term tangent, but I don't like that term because that usually implies horizontal, okay? The gradient is specced out in terms of the percent grade that it rises or falls on, and then it's based on an elevation, horizontal distance, and then you have also elevations up or down based off of that. Vertical curves are parabolic. So instead of dealing with a circular arc, now you're dealing with a parabola. So the math seems a little trickier because you're dealing with a polynomial, but it's actually real simple once you write out the equation for it. So we'll be going over that. They have what are called equal tangent parabolas and unequal tangent, and I'm not going to show you the unequal. I've got some diagrams in there, but we're only going to work with what's called the equal tangent parabola. Okay. So this is kind of the example of how vertical curves work with an alignment. So that green, notice, is your existing ground line. This is increasing from left to right. So we have that first gradient coming in. He's hitting a point right here called your PVI, point of vertical intersection. And then you have gradient 2 going out, then another PVI and a gradient going out. So it's basically line, line, line with gradients connected. So because your curve, your vehicle's not going to hit this dip and then just jump down, they put a little parabolic curve here because they use a parabola because it's easier to calculate elevations on, and it's also a smoother ride on a vehicle than it would be if you did a circular arc. So you could use a circular arc there, Some countries actually do that, but North America, we pretty much always use parabolas. The other thing is the parabola is usually defined by a distance from the start of the parabola to the end and the start to the end. Okay, so we'll get here in a minute to what all that means. Okay, so gradients are defined by 3 elements: the horizontal distance, either in feet or meters, or stations, elevation in feet or meters, and the grade or slope. Now that's typically spec'd out in percent grade. Could be unitless, but usually on plans you see it out in percent grade. So we need to make sure we know how to calculate that. So percent grade G is defined as your change in elevation, delta elevation, that's usually in feet, could be in meters, divided by your change in horizontal distance. And then you multiply that by 100. Okay, so if you leave it in feet per foot, it's not in a percent grade. So to express it in percent grade, we're going to multiply it by 100. An uphill number indicates, is indicated by a positive grade, and a negative indicates a downhill grade. But basically a 2% up and a 2% down is the same. It just depends on whether you're looking uphill or downhill on it. Okay. So when you see a number that says 2%, it says for every 100 feet of run that you're traveling, you're rising or falling 2 feet. Okay, so that's how a percent grade works. Okay, so before we get to this, let's do this real quick. I need to make sure you guys all know how to calculate these grades, because this is really, really important as well. So let me grab this guy here. Okay, so I'm going to clean this up. We're going to just do a real quick calculation just to make sure everybody knows what I'm talking about. All right, so I got a slope line that's doing this. I know that this is at station 500. Well, let me do it. This is at station 5 plus 0, 0 at elevation 800. This is at station, I don't want to make this too big, 820 point, let's do this. We'll say 821.26. And we're at station, let's say we're at station 7 plus 52, 06. What is the percent grade here? So how do we solve that? Well, what's percent grade defined as? What?
Rise over run.
Okay, so in this case, the rise is the elevations, right? Delta elevation. So percent in this case, percent grade is going to be equal to the rise or run. Now, are we going from, we need to know whether we're going this way from 600, from 5 to 7 or from 7 to 5. So let's say we're going from 5 to 7. So in this case, it would be the final grade minus the initial grade. Okay, so it's kind of like when you do inversing, because that's going to establish for you, I'm sorry, I did that wrong. I really want to go. I got this picture wrong, don't I? I got this picture wrong. Let's change that. Sorry about that. No wonder I wasn't getting a negative. Instead of making that, let's make this something different. I was thinking negative and it wasn't coming out negative, so let's do this. Let's make this 791.62.26. Okay, so percent grade is final minus initial, so we have 791.26 minus 800. There's my rise. And my run is going to be my final station, which is 752.06 minus 500. And we're going to multiply this by 100 because we want that in terms of percent grade. Okay, so we've done this with pipes a little bit, that kind of stuff, but highways do it the same way. So let's see what we get. 791.26 minus 800. That gives me a negative number, which is what I want to see. Anybody get a number for me?
I got 1.16.
I got a minus 3.47. Might check that number. See if you
Oh, I
got.
see what I did wrong.
Okay. Just make sure that you agree with me, okay? Let me check mine again. It could be on my end too, so I'm not 100% on my number until I check it twice. Yeah, it's 3.47%. Okay. So this is a kind of typical problem that you're going to see on these things. So you need to know how to do these. Everybody okay, Nat? Did you get that now, guys?
Yep.
Yeah, that's what I got.
What's the negative indicating?
The slope's going downhill.
Yeah, you see why I had to change my picture before, right? Because I had it down and what I had it high going the other way. So my picture would have been real incorrect. Okay. All right, so that's called your gradient slope. All right, so hopefully we're going to get some more of those. So, but just make sure that you're okay with that for now. All right, so let's go back into here. All right, so when we talk about gradients, the gradients are very simple. They just have the the plus value number or the minus value, but remember they're in percentage. Now, when you insert, let me go back a bit. Okay. So when you insert a curve, a parabola, there are two types of curves that you can have occur, what's called a crest curve or a sag curve. So a crest curve is where you have a high point on the curve. Not always, because it says may develop, so you don't always have high points actually on the curve. They might be further out on the tangent. And then you're going to calculate this thing called the rate of change of grade, R. For crest curves, whether they have high points or not, they're always going to be negative. Okay, so they're always negative. Sag curves are going to develop a low point. They're going to hold water. Okay, and that's a really important thing because that's going to be where you need to define where that is, because you have to put catch basins at that point to catch water. So when you guys are driving down the street sometime and you hit a dip, look left and right when you think you're at the dip, and you're going to notice there's catch basins there. That'll be 100%. If there's not, that roadway's flooding. But not all sag curves will develop low points because you might have a tangent that's lower than that. Okay. But these guys will have what's called a positive R value, and I'll show you what those mean here in a sec when I talk about R. So this is an example of a crest curve. So notice we have a positive grade meeting at a negative grade. And you can notice this guy somewhere along this thing is developing a high spot. Now, it doesn't have to be right in the middle of it, okay? It depends on what your grades are. If this is a positive 2% and that's a negative 2%, it will be right in the middle. But if this was a positive 5%, negative 2%, it's going to kick it one way or the other. Same thing with the sag curve, negative grade to a positive grade. You're going to get a low spot develop. Okay, so this is what I'd call the classic crest and the classic sag curve. Okay, so parabolas, parabolic curves, most people just call them vertical curves, VCs. They have 6 elements that define them. The grade coming into the curve, which is sometimes called your back tangent, that's your G1 grade. The grade going out in G2, the length of vertical curve. So this is the length of the vertical curve horizontally measured, not the arc length of the parabola. We never ever talk about that on a parabola. We only talk about the horizontal distance. So that also keeps it simple. That's your station distances. Algebraic grade difference is the difference between the grades 1 and 2, AD it's called, and then your rate of change of grade, and then there's another offset called your E. So we don't use E too much, but we will use all these other guys in here. There are some neat things about parabolas are very symmetric. So they also have real significant stations. Your BVC, which is your beginning of your vertical curve, and your EVC, which is your end of your vertical curve, and PVI, which is the point of vertical intersection. Some people call the BVC the PVC, point of vertical tangency, and some people use the term PVT for end of vertical curve. I think the set of plans I just showed you, they use PVT and PVC. So it just depends on where you work and whatnot. Again, that tends to be regional, all right? So there's a diagram here that interrelates all of this. So this is a schematic of a parabola. Okay, so here's your back tangent, your grade 1 coming in, it meets at a PVI, your grade 2 going out, and it ends at the EVC. The length is the distance from that point, your BVC, to the EVC measured horizontally, not this way. Okay, that distance right there would be the chord of the parabola. We never talk about the chord of the parabola, and we never talk about this bin distance of the parabola. Okay, we only talk about this distance, which is the horizontal distance. Okay, also notice if you drop a vertical line from the PVI down, straight down, it bisects L. So you have L over 2 and L over 2. So this curve is called equal tangent, okay? Because this distance and this distance is the same. Now, the weird thing is this is more or less your tangent, but that's not the same distance as this. They just refer it to this is called an equal tangent this way, okay? Not equal tangent this way, all right? So we're going to show you how to do some of these calculations. But what this is showing you is how the math works in a calculation of this. So normally also what we're interested in with this parabola is determining what would be the elevation at that point, or what would be the elevation at that point, or what I'm showing you is actually the elevation at this point right here based on the distance from the BVC to that point. So when you calculate parabolas, you're always looking at that distance from BVC out. That little guy E, by the way, is the distance. If I measure the distance from the PVI to that point on the curve, that's E, and from the PVI to that point on the chord, that's also E. So parabolas are always symmetric. This number and this number will always be the same for all parabolas. So basically that's your middle ordinate and your external when we were talking about that on circular arcs. That's kind of what that works as. All right. So there's a couple of key equations. We'll go through here. So when you're calculating a vertical curve, you calculate usually what's called the algebraic difference. And this is grade 2 minus grade 1. Now, when you do this equation, we have to be really, really careful. If this guy has a negative grade and this guy has a negative grade, it's going to be a negative minus a negative. So this actually turns out to be a plus. Okay, so you have to do it algebraically. And we always express the grades in percent. So we don't divide them by 100. We just keep them full blown. The rate of change of grade is your algebraic difference divided by L, or like that, or grade 2 minus grade 1 divided by L. So this is telling you how much that parabola is changing in terms of foot distance that it's traveling. So this is similar to your degree of curve, more or less, kind of like that. You can kind of think of that. Kind of works the same way for you. Your equation of parabola then is going to be r over 2 times x squared plus g1x plus BVC elevation. So once you write this equation out, you can solve any value along a parabola that you need. Okay, so that's pretty simple and straightforward from that standpoint. Okay, so I'm going to run through an example and show you how to do this so that we can work some numbers. And then I have some homework problems that I want you to look at for Thursday. And we'll take a look at this on Thursday. Okay, so let's take a look at an example here. So here's a sample problem. So we're given a vertical curve, grade in, grade out. We have an L and we have a PVI station and a PVI elevation. And what we're going to do is solve some things for this curve, okay? And let me flip it over to the other board here. So if you have any questions while I'm doing this, just stop me, okay? So the first thing I always do when I have a problem of this nature, I'm going to take the information that I'm given and I'm going to sketch it out, okay? So let me list out what was given. So we were told that G1 was equal to a positive 1.25%. They told us also further that G2 was a negative 2 3/4%. PVI information was given to us. PVI, we knew it was 18 plus 00. That's the station. And we were also told that it had an elevation of 886.10. So if I draw a really quick, oh, we knew one other piece of information. They told us that L was 600 feet. Okay, so we need to know all of that. So I'm going to draw a real quick picture because I'm going to assume that I'm going from left to right in this picture. So from left to right, we got a positive % grade, and then it's coming down negatively. So our parabola exists somewhere between there. So I've got a parabola coming up here. This is going to be my EVC. This is going to be my BVC. This is grade 1, positive grade. This is grade 2, and this is my PVI. The reason I like to do a picture is because it really helps me solve this. Okay, so we also know that this is 600 here. Okay. So the first step in any problem like this is to solve the BVC information and the EVC, okay? So for the BVC, the station for the BVC is going to be equal to the station of the PVI minus half of L. Because the distance from here back is half of L. Does everybody see that? So what would that give us? 600 divided by 2 minus 1800 gives me a station of what? Anybody get that number? Anybody still out there?
1500.
Okay. One thing you'll notice also with horizontal curves, the PCs and the PTs are going to always start at really strange stations because there's no way to make things real equal and even. With vertical curves, we very often will force the PVI at a nice even station, and so therefore these guys are going to be usually nice stations. Okay. If a designer is not doing that, they're not a very good designer. They just make it harder for people in the field if they don't do it that way. All right, so the elevation is a little trickier. So the elevation of this guy is going to be equal to the elevation of the PVI times plus the drop from here to here. So how do we solve the drop from the PVI to the BVC? How would we do that? Anybody know? Well, you know the grade, right? G1 is 1.25%. So that's the slope, right?
Yeah.
So in this case, we're going to take the slope times the distance, and that's going to give me the drop. Okay? The slope times the distance, and what is this distance here? From PVI to grade to BVC is what? It's half of L, right?
300.
Yeah. Now, what we're going to do, this is a little tricky. We're going to keep the percents in percent grade, and we're going to convert these guys to stations. So when you convert to stations, all you're doing is moving your decimal place 2 places, or just divide by 100. So 300 feet in 3 stations is 3, or stations is 3. So I'm going to subtract the difference, 1.25 times 3 stations. So this is going to give me the drop in feet is what it's doing, okay? Why am I subtracting? Because the BVC is what? It's lower than the PVI, right?
Yeah.
So this is the drop, okay? All right. So we're going to take 1.25% times 3 stations. what that tells me is it's dropping 3.75 feet in that distance. So we're going to subtract that from 8, 8, 6, 10, and I get 882.35. Everybody agree with that? $35. Anybody get that number?
That's what I got.
Okay. So, and it makes sense that it's lower, correct? It has to be lower, right?
Yeah.
Okay. So EVC, we're going to do in a similar way. So the station of the EVC is going to be equal to the PVI station plus 6/2. So 300 feet plus 1,800 gets us 21 plus 0, 0. Okay. EVC elevation is going to be equal to the PVI elevation plus whatever the grade is, which happens to be a negative, times 3 stations. So we have 275 times 3. It's dropping from the PVI to the EVC in 300 feet. It's dropping 8.25 feet. So I'm going to subtract that from the elevation of the PVI, and this gets me 877.85. Okay, so everybody see what I done there? This right here is very important. This is a check, okay? So you need to be able to do all three, but the BVC station and the BVC elevation, you got to get that right or you get everything wrong. Okay? Is everybody okay with that?
My only question is, when you came up with that number 3 for the 3 stations, is that because you have the G1, the PVI, and the G2, or how did you determine to use 3 there?
Because if slope is defined as what?
Rise over run.
All right, so if you divide rise divided by run in feet, your slope is going to be feet per foot, which is unitless, right?
Mm-hmm.
But we are not expressed in feet per foot. We're expressed in percent grade. So that's feet per 100 feet. Okay?
Mm-hmm.
So it's a unit thing. So I could do this one of two ways, Casey. I could take this and convert this to feet per foot. So if I took 1.25, I would have to divide it by 100, which gets me a really small number, right?
Mm-hmm.
And then I would have to multiply that by 300. If you keep your percent grades at percent and you put all your distances into stations, it's a lot easier to use, okay?
Okay, because like just looking at it, I thought it would have been a 6 because the length equals 6.
Oh, you weren't questioning my percent.
Yeah, I was just trying to figure out, will that number always be 3? Is that a constant?
No. It's based on what L is.
Okay.
Okay, let's look here. No, it's never if we go from the BVC to the EVC, we say it's 600 feet.
Mm-hmm.
If you drop this line down from the PVI, this is always half.
I see now. That makes sense.
It's always half of L. And that's why I use 3 here and 3 here.
I get it now.
Okay, there is another type of parabola called an unequal tangent. Okay, so that means that this L over 2, these distances are different, okay?
Mm-hmm.
We're not going to consider that kind, okay?
Mm-hmm.
But yeah, you have both kinds on highways. You have equal tangent, which is what we're looking at, and unequal tangent. So for any curve, these numbers are going to be the same, but they're not a constant forever, okay?
Yeah.
Okay, good question. All right, so let's, the next thing we're going to do is calculate the rate of change of grade. So this curve is kind of like this. So is this a crest curve or a sag curve? Is it going to have a peak, or is it going to have is it going to hold water? Is it going to shed water or hold water? If you pour water on this, is it going to hold it?
No.
No. Okay, so this is a crest curve. So what I said before, this R has to have a negative value, okay? So watch what we're going to do here. R is defined as G2 minus G1 divided by L. Now, we're going to express these guys in percent, and we're going to express this guy in stations, just like we did before. So, what is G2? It is what? Negative 2.75, right? Minus a positive 1.25. You see that? Grade 2 minus grade 1. What is L?
600.
So in stations, that would be what?
6.
6. All right. Let's see what we come up with. I get a negative 0.6667. That is basically the percent rate that this parabola is changing. So in other words, if you put a tangent line and just drew the tangent line along this, it would be changing at a rate of 0.666667% every time you move that. So it's essentially telling you you're going to go from a 1.2% positive to a negative 2.75% on the slope of any tangent. Okay. So, but do you notice what I said? This is a crest curve, so this has to be negative right here. See this? It's negative, right? So that tells us we probably did it correctly. If you came up with a positive number there, it can't be, because this curve, that would be telling you that curve is going to hold water, and it can't. Okay, is everybody with me so far?
Yep.
All right, so now we're going to write the equation of parabola. I am going to move this information over here. So we have 21 plus 0, 0 at 87785. And the other information we know is that this is 15 plus 0, 0, and that is at 882.35. Okay, so let me erase this so I can do some more stuff over here. Okay, downside to this. All right, so the equation of parabola says this, that y being the elevation at any point on the curve, okay, and that's what that reference is, that's your elevation, is equal to r over 2 times x squared plus g1x plus BVC elevation. So if we put what we have in there, r is negative 0.6667 divided by 2 times x squared plus g1x. G1 brings its sign with it, so if that happened to be a negative, we'd be subtracting. Plus the elevation of the BVC, 882.35. This is called your equation of parabola. And for this parabola, it's only good for stations here, which x, at this point, x is equal to 0. And at this point, x is equal to 6. Because x is always the distance from the BVC to wherever you are on your parabola. And your parabola isn't bigger than 6 stations long. Okay, does everybody see that?
Yep.
So if you plug 0 into here, what's going to come out of this? If you plug 0 in for x, what's going to happen? This is going to go to 0. This is going to go to 0, and it's going to tell you that the elevation at that point is 882.35, which is the elevation of that point, which should make sense. If we plug 6 in for this x, what should we get?
877.85.
All right, let's see. That's exactly right. Let's see what's happening. We should get the EVC elevation. So let's see what we get. Okay, so be careful when you're doing this on your calculator. It's real easy. Remember, this first term is squared. The second term is to the first power, or not squared at all. Okay. Some of you guys might be able to program this on your calculator. If you have a yeah, I don't know. You might be able to. Okay, when I put 6 in there, I get y equal to 877.85. So that agrees. So what that tells me is that this equation is a good equation. Okay. So this now allows me to get any station I wanted to get on this parabola. All I need to do is solve the x value and plug it in. So what would be the elevation of station? Let's see, we'll go right here. Let's say that's at 20 plus 25. I want to know what is the elevation at station 2025? So who can tell me what x would be?
525.
And how are you getting that? I agree with that. That's great. How are you getting that?
2025 minus 1500.
Yep. And then you're dividing that by 100, right? Because you're converting it to stations.
Yeah.
Yeah. So if you take, it's always the distance from the BVC to whatever station you're going to, okay? Because it won't work going this way. This equation is not written going this way. It's going from the BVC to the EVC. So yeah, we said we just subtract these two, divide that number by 100. It gets me an x value of 5, oops, not 2. Gets me an x value of 5.25. We could plug that in here, and let's see what numbers we come at. This will get that would be the elevation of station 2025. Let's see what we get. This little problem is actually very cool because any of you guys that are taking calculus right now, this is kind of some of the stuff you're doing in calculus. And this is actually utilizing that kind of stuff. Let me see what I'm coming up with. You guys let me know what you get.
I got 879.72.
Okay, I'll be right with you. We'll check. Hang on to that number a minute. 879, what'd you say?
72.
879. Yeah, I come up with that too. 87972. Yeah, I agree with that. Now, notice it's a little bit higher than this one. Shouldn't it? Should it be, right? Shouldn't it be a little higher? Because we're up here on the parabola instead of down here, right? Okay, this little equation, once you can solve that little equation, it's going to do all your work for you, okay? All right, so we've kind of run out of time, but you guys can finish. What I'd like you to do is you can go through on the PowerPoints that shows you, how to do some of this stuff. And then we haven't talked about high points and low points. I'll show you guys how to do that on Thursday. Be prepared to go outside. We're going to just run out there and do everything we can. Like I said, it's going to take us a half hour to an hour max. Then we're going to come back in and finish things off. I'll have the test ones for you. I'll give those back to you. We'll go over that. Be prepared for a quiz. It won't be on vertical curves. It'll be on horizontal curves. And I'll have some labs for you as well. So anybody has any questions, then feel free to stick around. I'm going to go ahead and stop the recording. And I'll get that thing formatted.